Hi, my name is Ching and welcome back to Data Structures in C++. In the previous lecture, we talked about different types of linked lists and using them for different applications, such as polynomials and sparse matrices. But before we go further in data structures, we need another tool, recursion. Recursion is important in describing and implementing more complicated data structures, such as trees and graphs. Today, we're going to take a break and start talking about recursion and how to use it to implement factorials and Fibonacci numbers. Then we'll talk about the general form of recursion. So what is recursion? Recursion is just one way to divide a big problem into smaller subprograms. And this process can continue until the problem size is smaller enough so that we already know the answer. The advantage of recursion is that it has a clean implementation. Here, let's use a factorial function to illustrate how recursion works. Here's how we compute the factorial of n mathematically. If we use recursion, we can simplify it by calling the same function, but with different parameters. This is how we narrow down the problem. After that, we check if n is smaller or equal to 1. If so, we return 1. This is because the factorial of 1 and 0 are both 1. Now let's see how to implement this function iteratively. Instead of calling the same function again, we use a for loop. The recursive and iterative functions are both equivalent, so they will return the same value. If there is an equivalent iterative solution, why do we still need a recursive solution? The biggest advantage of using a recursion is that it's easier to write than a non-recursive solution. But on the other hand, using a recursive solution is sometimes less efficient than a non-recursive solution. This is for a couple of reasons. First, if you use too many recursive calls, there might be a stack overflow, because function calls are managed in stack memory, which is limited. This means that the stack memory is full and cannot hold any more function calls. Second, it is very hard to debug a recursive function because the function enters itself many times. It is hard to keep track where the problems are. Last of all, if you're not careful enough, you might repeat a computation many times without noticing. This is an example of using recursion to implement Fibonacci numbers. Fibonacci numbers start with 0 and 1. After that, every number is the sum of the previous two numbers. For example, 8 is made up of 3 and 5. For recursion, 0 and 1 are both base cases. Then this will be the formula for the rest of the Fibonacci numbers. This is the recursive implementation of Fibonacci numbers. Here we check for the two base cases. Then we return fib n minus 1 plus fib n minus 2. This recursive solution looks very nice and clean, but it's actually a very inefficient way to implement Fibonacci numbers. Let's see why. When we use recursion to implement Fibonacci numbers, we have to make a lot of redundant computations. This means that we repeat the same task many times, even though we don't need to. This diagram shows the function calls involved when calling fib n. At the first level, it recursively calls fib n minus 1 and fib n minus 2. Then moving down, it continues to make more function calls with different parameters. But there are many redundant computations. For example, we repeat fib n minus 2, fib n minus 3, and so on. So if the recursive solution is inefficient, then what about the iterative solution? First, we make an array of size n plus 1. We set the two base cases 0 and 1. Second, we make a for loop and fill in the rest of the values. At the end, we return the last element in the array. By recording the previous results, this solution doesn't do any redundant computation, so it is much more efficient. It takes a while to get comfortable with recursion, but every recursion can be summarized into a general form. First, we need a stopping condition and a stopping value to return. Second, we call the same function again with one or more smaller problems. Here we use recursion to implement another example. We're going to find the summation of all the nodes in a singly linked list. First, we have the stopping condition and the stopping value. That is, if we already reached the end of the linked list, then we can stop there. Then we call the function again to narrow down the problem. Or specifically, we take the data from the head and call the function again with the rest of the list. In summary, we learned that recursion is a function which calls itself with revised parameters in order to solve smaller problems. It may look clean, efficient, but on the other hand, it has a few limitations, so you need to be careful. In the next few lectures, we will use recursion to implement some data structures, such as trees and graphs. This concludes today's lecture. Have fun and happy coding. I'll see you next time. Bye.